Welcome to this second video in the series of videos on electromagnetic induction. Just a quick recap of what we talked in the previous video. In the previous video we talked about the idea of flux, and we said the flux for a magnet, the flux for passing through a coil is given by the magnetic field strength due to a magnet. Let's say the magnet is here at 1. So due to its position, there is a magnetic field strength B at the coil. So if that is B1, so we say that B1 into A gives us a flux when the magnet is at 1, and B2 into A gives us a flux when the magnet is at position 2. If we know the time period at this position is T1 and the time period at this position is T2, and this whole movement happened in time delta t, we say that the rate of change of flux is given by delta phi by delta t, or in delta phi being phi 2 minus phi 1, which is changing flux by changing time. So that's what we talked about. In this video, we're going to continue the discussion and talk about Faraday's law and Lenz law. So let's first make the statement here. So what Faraday's law says is a changing flux, a changing flux. What does it mean? A changing flux means your delta phi is greater than 0 or less than 0, greater than or less than 0, right? It's not equal to 0. So maybe we can write that delta phi is not equal to 0, right? Now let's look at the coil. So in this particular coil, if this magnet was stationary at point 1, then your delta phi would be 0. So what we are saying is this magnet is not stationary. So if this magnet is not stationary and it is moving, so that's when there will be a changing flux through a coil, produces EMF. That means that it produces current in the coil, right? And the EMF is given by the rate of change of flux. We say this is rate of change of flux, right? So this is what Faraday's law states. Now, of course, this delta t determines how fast we move the magnet, we move the or how fast the flux changes, right? How fast the flux changes, how fast the flux changes, and delta phi implies the change in the flux. And let me make the statement here. This minus sign here, it indicates the EMF produced opposes the change of flux. Okay, so this sounds very abstract so far. So this is the definition. Now let us interpret this definition in varied context. Okay, so I think that will make this make this whole definition clear. So let's assume that you have here a coil. Of course, there are many coils, so we put only a few coil. And let's assume that you have this magnet coming here towards this at a velocity v, right? At a velocity v. So it's coming towards the coil. So as you can see, as it comes towards a coil, there is a magnetic field lines linked with a coil. So you can see those magnetic field lines that are linked with this coil, right? Let's say that this is linked with a galvanometer. So this is linked with a galvanometer, right? So the question is, so what does Faraday's law says? It says that the changing flux, that means as the magnet is moving towards a coil, the flux lines through the coil, which is delta phi, is increasing. So there is more flux lines as it moves from this position 1 to, let's say, position 2. So the flux lines are increasing in this direction, right? The flux lines are increasing in this direction. So Faraday's law says that then EMF is produced in the coil. So EMF is produced in this coil. There's a galvanometer which shows current. So without any battery, there will be current flowing in this coil. That's what Faraday's law says. Here you see, right? A changing flux through the coil produces an EMF. So there's an EMF produced in the coil. And the EMF produces such that it opposes the change of the flux. So if the flux lines are increasing towards the left direction, then the EMF produced is such that, you know, if you need to oppose change of flux, then the way that can happen is a current is produced in the coil. So on this coil, so I'm just drawing just one to represent the idea. So current is produced in this coil such that it opposes the change. So I want to oppose this increase towards the left by making a flux lines opposing that change. So how do I oppose the change? The only way I can do that is by passing a current. Only when current passes, then there is a magnetic field in this direction, as shown. So a current will be produced such that it will oppose the changing flux. So your current will be produced like this, so that it opposes the changing magnetic flux. So that's what it says, and that is the significance of this line. It opposes the change of the flux, and this minus sign over here, which indicates, you know, EMF produced opposes change in flux, is called Lenz law. So this is called Lenz law, and this part, what you see here, which is EMF is delta phi by delta t, is called Faraday's law. So this one equation packs both the law, right? Now let's look at a couple of more scenarios before we end this module. So if, let's say, for example, you have the same coil. Oh, by the way, I'm sorry. So the current here we say is being produced so that the current is flowing like this and coming back like this, right? So current is moving like this and coming back like this. Let's say the current is coming back like that. So what that means is that your galvanometer is going to show a deflection towards the left, right? So let us see the second scenario. So we have again a galvanometer connected, and you have this magnet, but this time you're moving in the opposite direction. So what happens is the flux lines which are through this solenoid is being reduced. So the flux lines are like that, but you will see that your flux lines are reduced in this direction, right? I mean, the flux lines will remain to be there as I move this from position 1 to position 2. So the flux lines will continue to be directed towards the left, but you will see the flux lines through the coil is reduced. So now to oppose that change, that it is being reduced towards the left, the coil would want to have flux more flux towards the left side. So it would want to have more flux towards the left side so that it can oppose that decrease of flux lines. And the way it can do it is by passing current the other way. So we say that, hey, the current is passed in the other way, so that, you know, the flux lines, it resists the changing flux line in that direction. So we say that, we say that the, you know, in this particular case, the current will move like that. So your deflection is towards the right, unlike the previous case. Well, we can extend further this idea by talking about two more cases, and I would urge you to pause this video here after you see the question and try to solve the problem, right? So let's say that you have galvanometer here. So the question is, let's say you have the south of the magnet and you are moving towards the left, and in the second case you have the same coil, but you are moving the magnet, you're pulling that magnet towards the right. So I would urge you to pause the video and try to solve this question in your mind. So pause the video here. Here is the solution. As the magnet is, in this particular case, we see that all your magnetic field lines are moving towards the south, and as you bring this magnet closer, you will see that the phi is increasing, right, through the coil, but it is increasing in this, the direction of the magnetic field lines are in this way. As a coil, you don't like the change. The coil does not like the change, which is increasing magnetic flux in this direction. So it opposes, it would like to oppose that buildup of the flux by producing flux opposing that change, and for that it needs to produce current in this way, and that's what you see here. The current is in this direction, and so the galvanometer would show the deflection towards right. And in the second problem, it's exactly the opposite. You have a situation wherein your flux lines are decreasing as you pull this magnet away. The flux lines are decreasing in this direction. So the coil, it does not like the decreasing flux in that direction. So to oppose that decrease, it produces current such that it builds up the flux so that it keeps the flux constant. It doesn't want the flux lines to decrease. And that it can do by producing current in this way. And that's why you will see current in this way, and the galvanometer shows deflection towards the left in this case. So here's the summary. The EMF, if there's one equation that can summarize this whole session, it is EMF is minus delta phi by delta t, where delta phi represents changing flux and delta t represents the speed at which it reduces. So more faster you move these magnets, the more EMF it's produced. So I hope you enjoyed this video. In the next few videos, we will look into some of the applications of Faraday's law. So until then, see you. Take care. Bye.